Perfect. So, the notes are visible, right?
Yes.
Okay, perfect. So now we saw in previous video. So the story was we have our sample and hold, and we have a sinusoidal input to our sample and hold. So whenever we design a sample and hold, and we have to characterize it, so there is a test which is a sine wave test. So basically, what we are doing is we are giving a continuous time input, which is a sine wave, and we are observing the output. So if at the output, we have to check whether the sample and hold we have designed, it is linear or not. So basically, we want our system to be linear to work properly. But then in previous videos, we saw due to some noise or due to some non-linearity of the switch, let's say, there was some kind of distortion we saw in the output. So that what our output basically tells us is if there is some kind of distortion, then we can see it in the form of non-linearity. So basically, we can say that if our system has to be linear, then its output should not be distorted or its behavior should be linear. So how do we categorize, or how do we prove that whether our system is linear or not? So in reality, it's not possible to make a system 100% linear. There will be some real problems which will make the system some kind of non-linear. But then how do we describe that our system is linear or not? So when we look at the output, if we are getting the harmonics for the input, then the system is non-linear. But the level or the bar or the value of harmonics tells us how much the system is non-linear. So what we do is basically we give an input of a sine wave, and we try to analyze and we check with how many harmonics are we getting, and are they passing the required threshold or not. So we set a upper bar or upper threshold for the harmonics, and we make sure that they are in check or they are not exceeding that threshold in order to our system to work properly. So what we do is now we have a sinusoidal input to our sample and hold. So in the output, we will get a sample of sequence, which is also a sinusoidal. But as we know, not all sinusoidals. So basically, we will be giving an input as a continuous sinusoidal. And after sampling at a frequency of Fs, we will get output, which is again a sinusoidal in a discrete domain, or basically it's just a samples of sequence. So we know that whatever output we are getting, uh, so for a discrete sinusoidal wave, it's it's not necessary that all discrete sinusoidals are periodic. So when we talk about the term periodic, so we need our output to be periodic. So why do we need our output periodic? First thing. So we compute the Fourier series and look at the coefficients of it in order to realize the strength of the harmonics. And to compute the Fourier, we need the sequence to be periodic. So then we saw how to design a condition for our output sinusoidal sample to be periodic. So this condition comes out to be this, which is Fn by Fs should be some integer divided by number of bins. So we talked about all the factors over here, how it arrived. So then we have this condition to consider when we select the frequency of input sine wave to characterize our sample and hold. So then we say that we have a periodic signal at the output, which is x of n. So this may be decomposed into a discrete Fourier series. So when we decompose this into a discrete Fourier series, and we looked at the coefficient of the Fourier series, so basically the Fourier series will be a periodic with two nonlinear coefficients, one corresponding to the nth bin. Sorry, here I said that one will correspond to the mth bin, not nth, and the other will be minus mth bin. So basically, this is when we talk about the Fourier series laying over minus n by 2 to n by 2. We can also take the condition where it lays from 0 to n, and when it is laying at 0 to n, then our two non-zero coefficients, one will lie at mth bin and other will lie at n minus mth bin, because at n by 2 there will be a mirror image of the components which is before n by 2. So what do I mean by this? So I demonstrated it by showing you the plots which we plotted using Python. So please let me know if the screen is visible or not.
Yes, it is visible.
Perfect. So let's say we took a case where we took this condition and we said that let's take our n to be 2 to the power something. So we took it 1024 in our code. So we can see our code. So we took the value of n as 1024 samples. So we now have from 0 to 1024 samples over these bins. But over here, what I have done is I have taken only half, because after n by 2, so this point is n by 2. So 512 is n by 2 basically. And after this point, we will just get the mirror image of whatever we have over here. So then we said if we see the two non-zero coefficients, so the first non-zero coefficient will lay at the point where there is m. So over here we have taken f in by fs as m by n. So if n is 1024, then m comes out to be 129. So at 129th bin, you can see properly, if this is 100 and this is 129th bin, we have a spike in the magnitude of the coefficient. So again, if it is at m distance from this side, then we'll talk about the case where we have three harmonics. So when we have three harmonics, then if we say that this is the 512th wind over here. So if this is a 512th wind, so this is the axis of symmetry, and everything after n by 2 will be just a mirror image of this part. So we are interested in this part, right? So let's say our fundamental lies at mth win over here. So what is m here again? So it is taken as 129. So our fundamental mth win is at 129 fs by n. So if it is from a distance of m over here, so from here it is n minus m, which is 1024 minus 129. So the mirror image of fundamental will be over here. But as we are only interested before the mirror image, I mean before n by 2, because after n by 2, everything is just a mirror image. So we have our three harmonics over here. And let's say our first harmonic is at 129. So basically at Fn. Then our second is at 2Fn. Third is at 3Fn. So even third lies before n by 2. So what if our fourth or fifth or let's say sixth harmonic will lie after the n by 2? So if it lies after n by 2, so it just gets reflect back to this portion. So let's say this is n by 2. So the amount of bins it exceeds n by 2, it again folds back, and the same amount of bin in the reverse direction, it lies on the uh, bin which is present over there. So I can show you by using this plot. So again, this plot is for the frequency 247. So we have our fundamental over here. This is 200, this is 247. So we have our fundamental at 247. Then we have our first harmonic, which is twice the value of 247, which is 594. And we know that this so basic not so basically this is our axis of symmetry, right? So 2Fn lies before the axis of symmetry, but the third fundamental lies after this, right? So the amount of bins after n by 2 at which fundamental lies, it get folds back and it comes at this bin. So this is our third harmonic. So this is our first harmonic, this is our second harmonic, and this is our third harmonic, which is folded back. And after n by 2, so let's say this is the n by 2. So after n by 2, we are just getting the mirror image. So this is how when we play, and I told you to play with the fin, right? So here the fin is 247 to be very specific. But then what happens? So I gave you a condition. I told you to take fin as 256. So when we take the fin as 256, so our Fin by Fs comes out to be 256 by 1024. So when our Fin by Fs over here comes out to be 1/4, the periodicity of the sample becomes 4 samples. So we said that all the odd harmonics aligns to the fundamental bin. So what does this actually mean? So this actually means that if the ratio is 1 by 4, then at 256 it will lie our first fundamental, and at uh, n by 2 we will get nothing, but after n by 2 again at 256th bin we will get our second harmonic. But as it is folded back again to the same amount of bins, so it will be folded back to the same bin. And if the harmonics are getting folded back to the same bin, then we will be having the aliasing of the noise, and then we will have the distortion. But as far as we are looking at the output, we can be misleaded by saying that, oh great, our sample and hold is having no harmonic, so it is perfectly real and it is actually perfectly linear. So that's a good output, but it is misleading, because what actually is happening is there do exist fundamentals, but those all are aligning either at n by 2 or at fundamental or at 0, which is DC. So in this case, we'll be having a aliasing of noise. So basically, if we analyze the same, so we analyzed it in the frequency domain. So if we analyze the same in the time domain, so let's say we put in a clean sinusoidal as an input, and let's say our sample and hold is very bad. So the worst case scenario is it produces a square wave um, with same frequency. So the output is a square wave for a input of sine wave. So the model we came across was this switch will be having some non-idealities, right? So and that will be in the form of the fundamentals of input voltage. So what we did was we considered the fundamentals of input voltage as in series with the input voltage, and then we took the switch as ideal. So this was our model, right? So basically what is it meaning is the nonlinear component of the sample and hold is actually a square wave which is being sampled by an ideal sample and hold. So therefore the obtained values after sampling will look like this. And by looking at these values, when we try to reconstruct the original continuous time signal. So over here, 2 pi represents 1024 if we take our similar case of 256 by 1024, and pi by 2 basically is 256. So it is m and this is n. So we have a sequence of 0, a, 0, minus a, again 0. So when we look at these samples and when we try to reconstruct the original signal, so it is given as sine of omega n, where omega is 2 pi by 4. So basically pi by 2. So it can be given by sine pi by 2 times n. So the plot is basically a discrete for the Fourier coefficient. We will get a big peak or big spike at pi by 2, and we can conclude that a clean spectrum is being sampled, and which can be misleading. So this can be misleaded. So basically this is a square wave which we are plotting, but we are getting misleaded that it is a sine wave. So actually sample and hold is distorting a sinusoidal by making it look like a square wave. Thus, by looking at the spectrum, we are not able to figure out uh, like that the bad things are actually happening in inside the sample and hold, because all the odd harmonics are arising back at the same bin as the fundamental one. So this is the problem. So we need to be very clear while choosing f in by fs ratio. But to fix this problem, we have to make sure that the harmonics do not arise onto either the input or any other harmonics. So what we are making sure is, so if this was our graph and these are the second and third harmonics, so we have to make sure the further harmonics should not get back allied to either the fundamental one or the harmonic, second or third harmonic, let's say. So they should not alias back to the same bin. That's what we need to make sure. So to fix this problem, we have to make sure that, and to make that sure, we can choose m and n such that they are relatively prime. So example, let's take this example that we want to characterize the sample and hold around Fn equals to Fs by 4. So basically, which is Fn equals to 256 by 1024 Fs. This is our case. So we can choose a relatively prime number which is close to 256, which is 247. So when we choose that, so this is the plot which is misleading, right? For 256. So the closest prime number to 56 is 247. So to analyze this, this is the graph we'll get. And over here, we can clearly see that this is our first fundamental. At 2 times f in, we have second fundamental, and at 3 times Fn, which is folded back, this is our third fundamental. So then we'll get a clear picture of what is happening. So this is the solution to this. So the takeaway, or for next video, I would like to uh, think, or I would like you guys to think what happens if, let's say, now you're clear that you have to choose this frequency as input, but this frequency is basically 247.00 hertz, but you'll have some fluctuations in your input frequency, right? So let's say what happens if it is 247.001. So please again play around this value in decimals now. So what happens when it is 001, or let's say 0001? So how is it sensitive to this fluctuation? So we will discuss this in the next video, and that's all for this video from my side. So if you have doubts, please do ask.